Alright, so we now start a new chapter which is going to be called metric space topology. So this course is primarily focused on analysis on the real line. However, what we are going to do is make a brief digression at this point and talk about how some of the concepts that we have discussed so far, specifically convergence of sequences, continuity of functions, and so on, can be extended to more abstract spaces than the set of reals. And specifically, we'll be working with the spaces that are metric spaces. Okay, so I'm going to define metric spaces more formally in just a bit, but intuitively metric spaces are abstract spaces where there is some notion of distance that is defined between elements of the space. Okay, and it turns out that so long as this notion of distance satisfies certain natural axioms, many of our familiar properties associated with convergence of sequences, Cauchy sequences, continuity of functions, a lot of these ideas can easily be extended so long as there is some notion of distance, that is some consistent notion of distance that is defined on the space. All right. So we begin by defining formally what a metric space is. So let S be a set and D be the so-called distance function. So this function is basically an element of S cross S, is a function from S cross S to R plus. What is R plus? This is 0 to infinity. And let this function D be such that satisfies the following properties. The first is that D of x comma x, which should be read as the distance between x and x, must be 0 for all x s, and D of x y is greater than 0 if x and y are not equal. Okay, that's the first requirement. The second requirement is that D of x comma y should be the same as D of y comma x. In other words, this function should be symmetric. And the final condition that the D function should satisfy is the following. D of x comma z should be less than or equal to D of x comma y plus D of y comma z. Okay, this again has to be true for all x, y, and z in S. Okay, so if you have a set S and a function D which takes two arguments of S and pops out a non-negative real satisfying these properties, then this tuple is called a metric space. Alright, and the function D is called either the metric or the distance function. Alright. So this is the definition of a metric space. Let's interpret that once again. So the set is S, right? And D is a function that must be defined which takes in two elements of S and pops out a non-negative real. That D is called a distance function and it must satisfy the following properties, right? So you should read D of x, y to basically be the distance between x and y, right? And the reason why you are in some sense justified in calling it a distance is because of property 2. right? Because d of xy is the same as d of yx, which means that the distance is symmetric between its arguments, and so it's meaningful to think of this as a distance between x and y, right? Once we understand d of xy as distance, the first property is something that has an easy interpretation. The distance between any point and itself must be 0. The distance between any point in S and another point which is different from itself must be positive, right? So between any two points which are not the same, there must be a positive distance between them, right? And finally, the third property tells you that if you take any 3 points x, y, and z, the distance between x and z should be less than or equal to the distance between x and y plus the distance between y and z, right? And this property, for obvious reasons, is also called the triangle inequality. Right? In two-dimensional geometry, we kind of encounter this, right? Where the length of any side of the triangle must be less than or equal to the sum of the lengths of the other two sides, right? So that motivates why we call this the triangle inequality, right? So essentially, the notion of distance must be symmetric. Between any two points which are not the same, there should be a positive distance associated between them, and the notion of distance should satisfy the triangle inequality. If these properties are satisfied, then we have defined a metric space. Okay, so let's do a few examples. The first example is, well, R is of course a metric space, right? So R with d, which is defined as follows: d of x comma y is simply the absolute value of x minus y, right? So this is a metric space. We call this d1, just because I'm going to use this particular function in another example going forward. A generalization of this is actually Rk, right? This is the k-fold Cartesian product of R, which means every element of this is basically a k-length vector of real numbers, right? So this is along with, let's call it dk, right? In this case, k is greater than equal to 1. So k is a positive integer, right? So this tuple is a metric space where I'm going to tell you what the definition of dk is. So this dk is defined as follows. Remember, dk is now being defined between two elements x and y, each of which is a k-length vector of real numbers, right? Each of which is a k-length tuple of reals. Okay, so this is going to be defined as follows. Now what is xi? Xi is the ith component of the vector x. Okay, so we define the distance dk as follows. The distance between 2 points in Rk is going to be defined as square root of summation xi minus yi the whole square. So you're taking a summation of the squared differences between the coordinates of x and y, and then finally taking a square root, right? So this has a name. This is called the Euclidean distance. Right, and this space is called the Euclidean space. Along with the Euclidean distance, we call this, so this pair, this metric space is called the Euclidean space. K-dimensional Euclidean space. you can see that R is in fact the space that we have been working with for the most part so far is the one-dimensional Euclidean space. Okay, now it's easy to see that this definition of the Euclidean distance satisfies the first two properties, namely that the Euclidean distance between two vectors is non-negative and zero if and only if the two vectors are identical. It is clearly symmetric between the two arguments. What remains to be shown is that the Euclidean distance between two elements of Rk satisfies the triangle inequality. Only then would this be a valid example of a metric space, right? So let me illustrate that. So I'm going to leave this as an exercise to you. Show that dk, which is the Euclidean distance, let me just remind you what that is. Dk of xy is equal to square root of summation xi minus yi the whole square. Satisfies triangle inequality. Okay, so I'm going to leave this as an exercise to you, except mention a couple of things, couple of pointers. The first thing to note is that the Euclidean distance is also related to the Euclidean norm. Okay, so we define the Euclidean norm of an element x as follows. The Euclidean norm is basically square root of summation xi square. Okay, so with this definition of this, so this is called the Euclidean norm. Why is there a subscript 2 which is sometimes placed on the Euclidean norm? That comes from the fact that we are actually taking the sum of the squares of the components before taking a square root, right? There are actually generalizations of the Euclidean norm which in turn lead to different notions of distance in Euclidean space, but that's not something we're going to talk about here. Okay, so with this definition of the Euclidean norm, note that the Euclidean distance is basically simply, so dk of xy is essentially just the Euclidean norm of x minus y, right? And so in this case, to prove the triangle inequality, it suffices to show the following. Right, so the Euclidean norm satisfies a certain subadditivity property, which it turns out is equivalent to the triangle inequality of the Euclidean distance. Okay, and as a final, let's say, hint or pointer to how to show this, I would also ask that you might want to invoke the Cauchy-Schwarz inequality. The Cauchy-Schwarz inequality is as follows. Summation xi yi, say 1 through k, is less than or equal to yeah. So again, I am going to leave this as an exercise to you. I've just thrown a few pointers at you, but the overall moral of the story is that I would like you to basically prove that the notion of distance that we have defined on the space Rk in fact satisfies the triangle inequality, which indeed in turn shows that the the Euclidean space Rk along with this notion of distance is in fact a valid metric space. Okay, so that brings us to the end of our discussion on the definition of a metric space itself. So having defined a metric space, I can immediately talk about what it means for a sequence in a metric space to converge. Okay, so let's do that next. So a sequence xn in a metric space converges to, let's say, some other element x in S if the following is true. Yeah, so we say that a sequence xn composed of elements in S where S comma D is a metric space converges to X if the following is true. For any positive epsilon you specify, there exists an n naught such that the distance between xn and X, the elements of the sequence, and X must fall below epsilon for all n greater than n naught. Right? So this is very similar to the notion of convergence that we are familiar with in the reals, because once I have a distance function, I have some notion of defining what it means for two elements to be close, right? So no matter what epsilon positive you choose, beyond a certain point, the elements of the sequence become less than epsilon distance from X, right? Which is being expressed as d of xn comma x is less than epsilon. Okay, so you can easily check that with d being defined as d1 that I defined in the example previous. This is in fact identical to the definition of convergence in R. Okay, so what we are seeing here is that once you have a notion of distance that is defined on the space, there is a very natural notion of what it means for a sequence in that space to converge. Okay, I want you to also stare at this definition and in fact convince yourself that this is in fact equivalent to saying that d of xn comma x converges to 0. Right? Remember, d of xn comma x is a sequence of reals. Right? So all I'm saying is that condition that I've written down, that for all epsilon greater than 0 there exists an n naught such that d of xn comma x is less than epsilon for all n greater than n naught. That's just a restatement of d of xn comma x, that sequence converging to 0. Okay, so this is what it means for a sequence in a metric space to converge. It turns out that once you have a notion of distance, it's also meaningful to talk about Cauchy sequences. A sequence xn in a metric space is Cauchy if, now remember what the definition of Cauchy was, that the elements of the sequence must get arbitrarily close to one another as you go further and further right. So that's exactly what we are going to enforce here as well. For any epsilon greater than 0, there exists some threshold such that if m and n are greater than n naught, then the distance between xm and xn must also be less than epsilon. Right? Again, you should be able to convince yourself that this is in fact a direct parallel of the definition of Cauchy sequences for real numbers, right? All you had is that instead of d of xm comma xn, you had mod of xm minus xn in the earlier definition, right? So this is a very natural generalization of the notion of Cauchy sequences in metric spaces, right? So once you have a notion of distance between elements, the definition of convergence of a sequence and Cauchiness of a sequence in fact follow quite easily. Okay. Now, a trivial consequence of the previous two definitions, which I'm going to state as an exercise to you, is that all convergent sequences in a metric space are Cauchy. Okay, this is just playing with the two definitions of convergence and Cauchy. So basically, convergence implies Cauchy. Okay, so this is something that we know is true in R. The proof is actually fairly straightforward, right? Because the definition of convergence means that the elements of the sequence, based on the distance metric that has actually been introduced, are becoming closer and closer to the limit x, right? But then you will have to use the triangle inequality to show that if these elements are getting closer and closer to x, they must also necessarily be getting closer and closer to one another, which is what the definition of Cauchy implies, right? So put these two definitions together, use the triangle inequality to argue that convergent sequences in a metric spaces are necessarily Cauchy. However, the converse is not necessarily true. It is no longer guaranteed that Cauchy sequences are convergent. So this is a property that we did have in R, remember, right? It was in fact a consequence of the least upper bound property of R, right? But in general, metric spaces, Cauchy sequences are not necessarily convergent. Okay, so I'll give you an example of this in just a bit. So it turns out that if a metric space satisfies the property that all Cauchy sequences are convergent, we call that metric space a complete metric space. If every Cauchy sequence in the space is convergent, right? In other words, if for every Cauchy sequence you can also identify a limit, right, then that metric space is said to be complete, right? So as an example, note that R comma D1, remember D1 of X comma Y is simply mod of X minus Y. Okay, so this is complete. Right? So we know that R, the way it was, in fact, it was defined in such a manner that it is complete, right? So we defined R, in such a way that it satisfies the least upper bound property, which in turn resulted in the completeness of R, namely that in R, every Cauchy sequence is guaranteed to have a limit, right? However, clearly, if you look at the space of rational numbers with the same notion of distance, this is also a valid metric space. This is not complete. Right? Because indeed in this space, I can come up with sequences of rationals which are Cauchy, however, they are not convergent. Right? In other words, there isn't an element in the set Q that the elements are getting progressively close to spite of the fact that they're getting arbitrarily close to one another. All right. So these are examples of complete and non-complete metric spaces. Another example that we will talk about next is in fact RK. Right, along with the k-dimensional Euclidean distance is also complete. Right. However, to kind of show this more formally, I would need to get into a few more details. So this is something that I'm going to move to the next lecture. Okay. So to summarize, what we have done is defined in this lecture a notion of the notion of metric spaces. So these are abstract spaces where there is a consistent definition of distance that exists, and this distance is basically something that is symmetric and must satisfy the triangle inequality. Right? Once you have this notion of distance, the ideas of convergence of sequences and Cauchyness of sequences follow easily. It also follows that convergent sequences are necessarily Cauchy. I'm sorry, I got it wrong. Convergent sequences are necessarily Cauchy. However, Cauchy sequences are not necessarily convergent. If every Cauchy sequence in a metric space is convergent, we say that that metric space is complete. Okay, and we give a few examples of complete and not complete metric spaces. Okay, so we'll continue this discussion in the next lecture, where specifically we will look at the k-dimensional Euclidean space and show that that is in fact complete.